Assalamualaikum. This is the continuation of video 4 from video pack 2 Zener Regulator. So we have done slides page 1 to 14 or 15 in part 1. So this is part 2. If you've not listened to part 1, please listen to part 1 first. So I'll pick it up here from the voltage regulator circuit analysis. So for the purpose of this circuit, for the purpose of this course, we will consider the simplest of the voltage regulator so that we have a general idea of what a voltage regulator is, and we will consider three cases. One, we will first we will see the operation of Zener diode where the value of the input voltage is fixed and the value of the load resistance is also fixed for the case 1. For case 2, now the whole idea of this voltage regulator is so that it can tolerate varying value of resistances that is connected to the voltage regulator, yet it can still maintain the same VL across the different values of RL within a certain range. So for case 2, we want to know what that range is. What would RL min be and what would RL max be? Okay, for case 3, we are investigating the ability of the voltage regulator, of the Zener diode in the voltage regulator, to tolerate variation in input voltage such that it does not affect VL that RL is supposed to receive. Okay, so case 1, when everything is fixed, we just want to see operation of the Zener diode. Case 2, we want to investigate the range of RL, and the case 3, well, don't take these cases so strictly, it's just so that I explain to you what the differences is. So case 3 is the range of input voltage that the voltage regulator can tolerate. So we will now look at first general overview of how to analyze a circuit before we go on to the actual example with values for the components. Okay, the first case, analysis for fixed values of Vin and RL. So if we have a circuit here with Vin, Rin, a Zener diode Vz, and a load resistance RL, if we look at the circuit, we will have to first decide, just as we did with the other diodes in the previous circuit, will the Zener diode conduct? Knowing that the behavior of the Zener diode, it will break down, but still will it conduct? Now, just looking at the value of V1 now will not be enough, like what we did with our previous circuits. It will not be enough because there will be voltage drop across Rin and other components as well. So if, let's say, for example, if I look at here, this is say for example 12 volts, and Vz will break down at 10 volts. Now this 12 volts will not necessarily break down Vz because there will be voltage drop here, and there is another path at the outer loop here. Okay, so how are we going to handle that? To determine if the Zener diode can break down with the supply values, first we have to analyze by removing the Zener diode from the network and calculate the voltage V across the open circuit, which is VL, using voltage divider rule without the Zener diode. Now, without the Zener diode, we will find this value V, okay, which is equals to VL, which is equals to RL over R plus RL times Vin, okay, without the Zener diode here, and we'll look at this value of V. This will tell us if the reverse bias voltage across the Zener diode is enough to cause the Zener breakdown or not. If we calculate and find that V is greater or equal to Vz, then the Zener diode will turn on and the equivalent model of voltage drop Vz can be substituted. Otherwise, if the voltage that we calculate is less than Vz, the diode is off and the diode acts as an open circuit. And we will do an example to illustrate this. So if the analysis in the previous slide has shown that the Zener diode will break down or can break down, if the circuit will cause Zener diode to conduct through the Zener breakdown, the load voltage VL will lock in at Vz. Okay, then we are ready to proceed with the circuit with the Zener diode in operation. Okay, so let VL is equals to VZ if it is shown that it can break down. Okay, so let VL is equals to VZ because RL is parallel to the Zener diode. Okay, once this one breaks down, then VL is now equal to VZ because they are parallel, and this diode will lock the value at the breakdown voltage VZ. Okay, and again, remember that the notation, okay, that the notation of VZ is positive at the negative terminal because it breaks down in the direction of current flow entering through the positive terminal. So VZ is positive at the negative terminal of the Zener diode. Okay. So, and the Zener diode, when it turns on, as soon as the voltage across the Zener diode is VZ volts, okay, when it turns on, the Zener diode will then lock in at this level and not allow higher voltages than VZ to reach the load. So even if Vn keeps on increasing, okay, VL will remain constant because it is in parallel with VZ that has locked at that value. Any other increase of Vin, the voltage drop will be across this input resistance R. Okay, so once we know that, we'll do a KCL at this node, this blue node here, where IR is equals to IZ plus IL. And therefore, from this equation, if we know VL and we know RL, then we can figure out what IL is. Okay, and if we know Vin and VZ, we can do a Kirchhoff's voltage law to find the voltage across R, and therefore find IR from Ohm's law. So we can use KCL to find the current through the Zener diode. And then once we know that, we can find the power absorbed, because if we have Zener voltage and we know the current through the Zener diode, we can find what is power dissipation of the Zener diode, and we can check against the device ratings PZM, because we must make sure that the power dissipation of the Zener diode must be less than the maximum power dissipation allowed. Okay, a proper example here with values. So we have a voltage here at 16 volts. The input resistance here R is 1 kilo ohm. The Zener diode has a breakdown voltage at 10 volts. We're supposed to find V out, which is the voltage across RL, VR, which is the voltage across the resistance R here, IZ and PZ, which is the current through the Zener diode, and the power dissipated by the diode for two cases of RL. One is 1.2 kilo ohm and the other is 3 kilo ohm. So now let's check at 1.2 kilo ohm. So if RL is 1.2 kilo ohm, what do we do first? We must check if the diode can turn on. We know that the Zener voltage breakdown is 10 volts and this power supply is 16 volts. So checking if Zener diode will break down, okay, we remove the Zener diode as suggested in our analysis in the few slides before this, a couple of slides before this. So we remove the Zener diode. Let's do the voltage divider rule. Let's have a look at VL when the diode is not there with a power supply of 16 volts. If we do this voltage divider rule between 1 kilo ohm and 1.2 kilo ohm for our load, we find that VL is 8.73, and 8.73 is less than VZ, which is 10 volts, which means Zener diode will not break down. Even though the Zener diode does not break down, there is still current in the circuit, except that the circuit does not pass through the Zener diode. It just goes through R and then RL. Okay. So circuit with non-conducting Zener diode will look like this. The Zener diode is now replaced with an open circuit. This is also an open circuit, but this was an analysis to find out if the circuit will be able to turn on the voltage. So here we have drawn the circuit with the Zener diode as an open circuit. Okay, and then we do we know that IZ is equals to 0 amps because this is an open circuit. with an open circuit, current is 0. We do KVL around this blue loop to find out VR. Okay, so we have negative 16 plus VR plus V out equals to 0, and V out is the value that we've calculated previously. If there is no Zener diode, is 8.73 volts, so VR is 7.27 volts. Okay, so the voltage across these two are comparatively around the same, and this is perhaps because R is too small for this circuit. Okay, R would have to be bigger to allow this Zener diode to break down, as we shall see in the next example when we treat RL to be 3 kilo ohm, because the next value we will see that the Zener diode can turn on. Okay, so anyway, we do KVL here. We have VR 7.27 volts. Let's finish up this question first. So the power dissipated is IZ, which is 0, times the voltage, the V open circuit, which is equals to 0.1. Perhaps there is a slight correction here. IZ is equals to 0, but the voltage across here is going to be the voltage open circuit. Never mind. Okay. Right. Here we have a circuit with RL equals to 3 kilo ohm. Now checking if the Zener diode will break down. If we check, the Zener diode will break down, in doing that we have to remove the Zener diode, just as in the example before, and we find that the voltage is 12 volts as opposed to 8.7 in the previous slide. So when it's 12 volts is more than 10 volts. Since breakdown value VZ can be reached, now in this example, when the resistance is bigger, the Zener diode will break down. Okay, so when we do circuit analysis with Zener diode breakdown, okay, let's redraw the circuit, and we have here IR, IZ, and IL for the currents. Okay, VR and V out for the voltage across the resistance, and the Zener diode is now VZ equals to 10 volts. Okay, so because 3 kilo ohm resistor is in parallel with VZ, and because VZ has turned on and locked its value at 10 volts, therefore V out is equals to 10 volts. And if I do a KVL along this green loop, I will get negative 16 plus VR plus 10 equals to 0, so the voltage drop across VR is 6 volts. Why am I doing all this? Because I want to know what IZ is, and before I can find IZ, I need to find IR first, and for me to find IR, I need to find VR. So once I find VR, I can do Ohm's law for the resistor R. So VR is equals to IR times R. IR is going to be 6 over 1K, which is going to be equals to 6 milliamp. And since I know the voltage drop across this resistance R, I can find the current. Is the same case with this 3 kilo ohm. I know the voltage across it because it's parallel with the Zener diode, and it's 10 volts. Okay, and I know that the value of this resistance is 3 kilo ohm because it's given in the question. So IL for the load resistance is 10 divided by 3 kilo ohm, so that should be around 3.33 milliamps. So when I do a KCL here, why am I doing KCL here? Because I know IR and I know IL, and I want to find out IZ. So IZ is going to be equal to IR minus IL, which is 6, which we found earlier, minus 3.3, which is equals to 2.67 milliamp. Then the power consumed by the Zener diode is VZIZ, so power is equals to VI. Okay, VZ, which is the voltage across the Zener diode, which is 10 volts, and IZ, which we found from the KCL earlier, which is 2.67 milliamps. So the power consumed by the Zener diode is 26.7 milliwatt, and 26.7 milliwatt is less than the maximum power rating given in the question, which was 30 milliwatt. So this is within limits, so the operation is all right. Okay. Case 2. Now let's find the range of allowable RL when the input voltage is fixed. Okay, so the same circuit, we're still looking at the same circuit, but the question is, let's say Vin, Rin, and Vz are fixed values that come out of voltage regulator as part of a DC power supply. What are the ranges of RL, or the system that is trying to drive? What are the ranges of RL can the regulator support? Okay, before we go on, again, the yellow screen, yellow background, we have to do some basic revision. Okay, we want to have a look at effect of elements in parallel towards current. These are basic stuff, right? I think you studied this in SPM, or maybe in diploma again, so, or in your foundation years. So you have Vin, and then you have R1, okay, connected to R2 that is parallel with R3. Now, why am I putting this circuit here? A circuit so simple for you, because there are some things that you need to know, that when you look at the circuit, you can decide intuitively, meaning you don't have to actually do your calculation. Just by looking at it, you can reason out how the circuit works. So yes, we know that we do a KCL at this node 1, which says I1 is equals to I2 plus I3. That is the Kirchhoff current law. Now, if R3 is larger than R2, how is V3 compared to V2? Can you respond to that intuitively? Well, the answer is V3 is going to be the same as V2, because R3 is in parallel with R2, right? So they are the same, V3 and V2. But how is I3 compared to I2? So if R3 is larger than R2, okay, current I3 is going to be less than I2. I don't have to do a calculation for it, because I know current will always find the path with a shorter resistance to pass through. So a lot of current will flow through R2 compared to the current that flows through R3. Okay? Or you can also think about it in the terms of Ohm's law. V is equals to IR, V is equals to R. V is the same. If R is big, I will be small, because V is equals to IR. Okay? So another question that you might want to sort out after you watch this video lecture as well, that you have to decide intuitively, is if R2 parallel with R3 as a combination is much larger than R1. Okay, so R1 is small compared to the parallel combination of R2 and R3. What can you say about V3 compared to V1? So meaning that R1 is small. Now, if R1 is small, okay, because the current through this circuit is going to be the same. So if I is maintained the same, if R1 is small, the voltage drop across R1 is also small compared to the voltage drop across R2 and R3. Okay, so if R2 and R3 is much larger than R1, V3 is also much larger than V1. Another thing that you should be able to see is if R2 and R3, which are in parallel, if both of them is too small compared to R1, V3 would also be small compared to V1. It's just the opposite what was said in the previous point. Another point is that if R3 is too big compared to R2, I2 would be much bigger than I3, right? If R3 is so big, okay, more current will flow through R2. And I think if you like to think about it mathematically, it means like you're thinking about it in terms of current divider rule. Okay, but if you're just looking at it, understanding that a lot of current will find a shorter, lower resistance path, okay, you can say intuitively that I2 would be much bigger than I3 if R3 is much bigger than R2. And if R total is small, okay, if we add R1 plus R2 that is parallel with R3 effectively, so you will find that if the R total is small, we can expect that I total will be large for the same Vin fixed. Okay, now play around with this resistive circuit, because we're going to use it here. So analysis when Vin is fixed but takes in a range of RL. So what is RL min and what is RL max? Basically, this question is that. So Zener diode requires reverse bias greater than Vz for it to conduct in Zener region. This means that there is a minimum RL that can be required to ensure Zener is conducting. Okay. So it has to be this Vz here. Okay. You need to have a minimum RL that will be required to ensure that the Zener is conducting. Earlier we did an example of RL. One is 1.2 kilo ohm, the other is 3 kilo ohm, and we find that at 1.2 kilo ohm Vz did not turn on, but when RL was 3 kilo ohm, then only Vz turned on. So meaning that if RL is too small, diode will not break down, will not turn on. So if RL is too small, VL will be less than Vz, and the Zener device will be in the off state. Now using this concept, this is where we need to find R min. Okay. On the other hand, if RL max is too big, okay, this is going to affect the Zener diode in terms of the maximum power current rating that it must not exceed. How is it that when RL is too big, that this Zener diode will exceed the power ratings? The answer is because the previous slide that we had, the yellow slide of the resistance circuit. Now if RL is too big, okay, the current that passes through RL is too small, and therefore most of the current from IR will be flowing through IZ. And we have to watch this value IZ, because IZ times Vz will give us PZ. Now, and Zener diode is a sensitive device with maximum power ratings. We must make sure that it is not exceeded. If RL is too big, IZ will be too big and may cause the Zener diode to exceed maximum power ratings, and this is where the concept of R max comes. So when we calculate, first we have to consider R min, which means that we need to consider the voltage here, and the next one is to consider the Kirchhoff current law to check what IZ is going to be. Okay, now let's start with RL minimum. To determine the minimum RL that will turn on Zener diode, we will use the same concept that we had with case 1. We need to find the value of RL that will result in a load voltage where VL is equals to Vz. Okay, so in the first case, because RL is fixed, we removed Vz and we find what RL is, what VL is, right? So if VL is greater than Vz, then we say it will break down. But in this case, we're trying to find the range of RL. So we know that when we remove the Zener diode, we'll have to set VL to be at the minimum required reverse bias Vz so that it breaks down. So we allow the same thing, VL is equals to RL times Vin over R plus RL, but in this case, for the case of RL min, we set VL to be equals to Vz. And when, like this, okay, we set VL to be equals to Vz. In our first case, we found the value for VL and we compare it with Vz. But here we set it to be equals to Vz. And when we set it equals to Vz, we can find RL min. And when RL min, okay, the minimum RL will establish the maximum IL. Because of Ohm's law, okay, I is equals to V over R. If R is minimum, that means I is maximum. Okay. So we can find IL max or RL min. So the procedure is first remove the Zener diode, let VL equals to Vz, find RL min using voltage divider rule, and then find IL max using Ohm's law. Then R maximum. Now in the previous slide we found RL minimum, now we want to find RL maximum. So we have the same circuit. Okay, once the diode is in the on state, the voltage across R remains fixed. Why is it saying this? Because when we do Kirchhoff voltage law, once this diode turns on, okay, the voltage drop across this diode is going to be Vz. And Vin is also a constant value. So if we do a KVL here, you're going to find a constant voltage across R. And because VR is fixed and R is fixed, IR is also fixed. Okay. What am I getting to here? Okay, I'm getting to here is that if IR is fixed, okay, we can find a maximum value for Z and IL, because how IR is distributed between the RL and the Zener diode depends on the value of RL. Okay, resulting in a minimum IZ when IL is a maximum and min, and a maximum IZ when IL is the minimum, since IR is a constant. Okay, so again, as I said just now, I'll repeat myself, IR will distribute to IZ and IL. Now the distribution between IZ and IL will depend on the value of RL. If value of RL is too big, okay, then there will be a minimum value of IL, because if RL is too big, a lot of the current would prefer to go through the Zener diode. So at IZ maximum, as determined by power ratings or stated in the maximum current, okay, we can find IL minimum is equals to IR minus IZ maximum. So IR comes from the fact that it is a fixed value based on the circuit, and IZ maximum will come from the data sheet, or the question will state it for us. Okay, so from Ohm's law, at IL min, okay, if we do an Ohm's law here, RL max is equals to VZ divided by IL min. So the thing is, find IL min first, then do Ohm's law to find RL max. Okay, ready for an example? Okay, we are given here V in of 50 volts, resistor R is 1 kilo ohm. The Zener diode is a 10 volts with IZ maximum 32 milliamps. We're supposed to find the range of RL, and we want to find the maximum voltage rating of the diode. Okay, to find the minimum RL first, okay, so we need to find minimum and maximum. We'll find the minimum first. Minimum of RL means that we know we need to find when the Zener diode breaks down. So we will let VL is equals to VZ, which equals to 10 volts, because that's the value at which is minimum for the diode to break down. So when we do a voltage divider, this was explained in just the previous slide. Okay, VL, we have an expression of RL min divided by RL min plus R, the whole thing multiplied by V in, and we let it to be equals to VZ. Okay, and then we rearrange to find RL min, and we find, putting in the value of R to be 1K, VZ to be 10, and V in to be 50, the value is 250 ohms. And for this example, that is the minimum value of RL that will cause the voltage to break down. Otherwise, the the voltage regulator will not be functioning as it should. So the minimum value should be 250 ohms. If you want to connect anything here, it has to be bigger than 250 ohms. Okay, if we know that it's going to be 250 ohms, now the next thing is we need to find the maximum RL, and maximum RL will occur when IL is minimum. Okay, so to find the IL minimum, first we need to find IR here, because just now we said the current at the IR at this point here will branch out to IZ and IL. Okay, IR is fixed once this diode turns on, because when we do KVL, we'll find VR. The voltage supply is fixed at 50. The Zener diode locks at 10 volts. So VR is going to be a fixed value of 40 volts, and using Ohm's law, we find IR to be equals to 40 milliamp. Now when we do KCL at this point, okay, IR is equals to IZ plus IL. If IZ is the maximum, then IL is the minimum. Okay, so we find IL minimum to be 8 milliamps. Now if IL is a minimum, using Ohm's law, okay, if the number that you divide is IL is minimum, then RL max is going to be 10 divided by 8 milliamp, which is going to be 1.25 kilo ohms. And the power ratings for the diode is VZ, which turns on at 10, times IZ max, which is the value that they give, which is 30 milliamps, to be equal to 320 milliwatt. Okay, So summarizing, RL min is 250 ohms, RL max is 1.25 kilo ohms. Okay, if you supply anything less than RL min, the Zener diode will not be functioning, will not be conducting, and the regulator will not be doing its job. If you supply more than 1.25 kilo ohm, the Zener diode will be exceeding its power ratings. Okay, and PZM is 320 milliwatts. Case 3. This is a different case. In this case, the same question, the same circuit, but the question is different. The question is, what are the variations of Vin that the regulator can tolerate? So let's assume everything else is fixed value. Now in this case, RL is fixed, R is fixed. We just want to know this voltage regulator, what values of Vin can it tolerate? Okay, so we're going to, just like the range of RL, here we want to find the range of Vin. When is Vin a minimum and when Vin is a maximum? So for the fixed values of RL, the voltage Vin must be sufficiently large to turn the Zener diode on. Right? So if the supply voltage itself is not big enough, it cannot cause the Zener diode to break down. So in order to find the minimum value of Vin, we let VL equals to Vz, just like the situation before. But the minimum turn-on voltage Vin min is determined by, okay, VL is equals to Vz, which is equals to RL Vin R plus RL. But the previous case 2, RL was not fixed value. So in this case, RL is a fixed value. Okay, and we can find Vin minimum from the voltage divider rule rearranged. Vin maximum. The Vin maximum value is limited by the maximum Zener current IZM. Okay, how is that? Now since IZM is equals to IR minus IL, okay, IR max is equals to IZM plus IL. So let's have a look. Since IL is fixed at Vz over RL and IZM is the maximum value of IZ, the maximum Vin is defined by Vin max is equals to VR max plus Vz. Okay, so IR, if we consider the circuit, if we want to find Vin max, okay, because Vz is fixed, you can actually have VR to be as high as you like, right? Okay, but you cannot, because of Ohm's law. If you VR goes too high, IR will also go too high. So what's the problem if IR goes too high? Now if IR goes too high, it would be giving too much current to the diode, that the diode might be exceeding the power ratings. Okay, so let's do an example here. Determine the range of values of Vin that will maintain the Zener diode of the circuit here in the on state. Here RL is fixed at 1.2 kilo ohms. We want to find the range of Vin that this regulator can tolerate. So to find Vin min, Vin must be able to cause Zener diode to break down. So I'm just doing what was explained in the slides before. Okay, we remove the Zener diode, we let VL is equals to Vz, and then we do a voltage divider rule to find Vin minimum, and we find that the Vin minimum with all these values put in is 23.67 volts. Okay, I would recommend you to actually find pen and paper and do this yourself. Then only you will understand what this whole process is all about. So this is Vin min. To find Vin maximum, okay, now if we look at this situation, again I'm explaining it here again, but here I'm writing it on paper, okay, which means that if you do it, this would be a good way to follow it as well. So Vin max is limited by VR max, and VR max is limited by IR max, and IR max is limited by IZM. If it is not an issue, the Zener diode can accept a current as large as possible. You can have IR as large as possible or VR as large as possible, but that's not possible because all these devices have maximum ratings. Okay, and especially so the diode is a sensitive device, so you need to make sure that it does not exceed its power ratings. Sensitive in the sense of the maximum power dissipation. Okay, so IR max is going to be equals to IZM plus IL. So IL is fixed because RL is fixed. Okay, it will turn on at 20 volts for the Zener diode, so VL is equals to 20 volts and RL is a fixed value. So this is a fixed value, 20 divided by 1200. But IZM, you get it from the question. So IR max is 76.67. So to find VR max, okay, the maximum value of VR is 76.67 milliamps times resistance 220 using Ohm's law, so you get 16.87 volts. So that is the maximum voltage drop that R can take, okay, not because of R, but because if it takes any more than that, it would be causing too much current to flow across the Zener diode. So for regulator to function, okay, V in has to be less than 23.67. Okay, this is from the previous slide, and it has to be less than 36.87. Now I have not included in my calculation there. I think I missed out something here. So VR max is 16.87. So V in max is going to be, if I do a KVL around this loop, I'm going to get minus V in max plus VR max plus 20 equals to 0. So that means V in max is equals to 16.87 plus 20, which is 36.87 volts. Okay, so we've covered 3 cases there. One is just calculating straightforward the Zener diode operations. Second is we attempted to find RL min and RL max. And the third is we attempted to find V in min and V in max that the regulator can withstand. Okay, so we are now at the end of diode applications. Hooray, hooray, before we go on to bipolar junction transistor. So I'll just end with power supply block modules again, because this is, I think this is where we can actually put in most of the circuits that we have studied. Okay, starting with an AC voltage. Okay, we have an AC voltage that comes through the transformer from distribution. It goes through the transformer, then it goes to the rectifier. Okay, a steady DC voltage is obtained by rectifying the AC voltage. Okay, first we pass it through the rectifier, then we pass it through a filter. Because the filter is basically it can be a simple capacitor filter, so you can find across these power supply circuits huge values of capacitor, huge in the sense where you have to look at it comparatively, because the capacitor will cause torr, which is equals to RC, so the charging and discharging will somewhat improve the pulsating DC, but it will still have some kind of ripple before it goes through our Zener regulator, because our Zener regulator can tolerate changes in Vin, but it will maintain an output load at a standard DC value, and this DC value is VL, is that Zener voltage VZ. Okay, so a transformer is to step down the AC input voltage. A rectifier is a diode circuit that convert AC to pulsating DC, and we have covered half wave rectifier and full wave rectifier. And full wave rectifier we have covered 2. One is bridge, the other one is center tap transformer. The simple capacitor is not something that we did in our course here, but it's sufficient for me to say that you can use a simple capacitor. And a voltage regulator unit, which we just covered using Zener diodes, is used to produce a DC voltage with much less ripple and remain fixed regardless of any changes in the input DC voltage or load connected to the output DC voltage. So that's it. We will be meeting in the next video, which will be bipolar junction transistor. Thank you. Assalamualaikum.